Hello, and welcome to today's webcast brought to you by LEDs Magazine. I'm Editor-in-Chief Maury Wright. It's my pleasure to host today's presentation, Display Industry Reflects an Application-Driven Shift in Illumination Technologies. Our presentations today will come from Mike Casper, CEO of Flex Lighting, and Bob OBrien, co-founder and president of Display Supply Chain Consultants. We'll get started here in just a minute. I just want to make a few announcements and cover some logistics. The presentation is meant to be live and interactive, so you can ask a question at any time by clicking on the Ask a Question button in the presentation window. No need to wait until we get to a Q&A session. Just type it in as soon as it occurs to you. For your convenience, this presentation will be available on demand within 24 hours of the live event. We'll be sending you a reminder email with a direct link to it, although you can always get to all of our webcast archives from our homepage at ledsmagazine.com. Just go to webcast in the top navigation. And today we are making these presentations available for you to download in a PDF format. On the lower left of your console, you'll see a drop-down bar entitled Event Resources. Click on that and you can download the PDFs. Also, I just remind you that most people do watch these webcasts on PCs and browsers, but you can also view them on mobile devices. I'd certainly like to thank Flex Lighting today, who is our sponsor in making this presentation possible. We have a very exciting topic for you today. Display technology is really constantly evolving, and both solid-state lighting technologies, LEDs, and OLED technologies are fundamental to most of the displays that pervade our lives. And so today we'll hear about how those technologies are evolving and what's coming down the road. I'll briefly introduce you to our speakers. Mike Casper is founder and CEO of Flex Lighting, and previously was a consultant at ZS Associates. He earned an MBA from the Kellogg School of Management at Northwestern and an engineering degree from the University of Wisconsin. And Bob OBrien has long experience in engineering, product marketing, and business management related to display technologies. His work experience includes time at Philips Display Components, LG Philips Displays, and Corning Glass Technologies. And Bob earned an MBA from the University of Michigan and an engineering physics degree from Cornell. Bob, you're leading off. The floor is yours.
Okay. Thanks, Maury. This is Bob OBrien. I am the co-founder and president. The name of our company is Display Supply Chain Consultants, but we typically go by the abbreviation DSCC. So today I'm going to, first, after giving you an introduction to my company, I'm going to talk mostly about the display battleground for display technologies, which is smartphones. And there you see the battleground between LCD and OLED, which are the two main flat panel display technologies. Some interesting aspects of the Apple product launch yesterday plays into that. So I'll talk mostly about smartphones, but we'll address other applications and energy issues related to things with LEDs. And then I'll talk about an emerging display technology, which is not yet in the mainstream, but for which there's been a lot of discussion, called MicroLED, and talk about some of the advantages and the challenges and what we expect to see out of that technology in the coming years. So, Display Supply Chain Consultants was formed about 2 years ago. We have a close relationship with the Society for Information Display. That's what SID is, for those of you who don't know it. Launched at the SID conference a couple of years ago, and a predecessor to our company, Display Search. The founder of our company was also the founder of Display Search, who launched that in 1996. We have 4 founders of our company, 2 in the U.S. and 2 in Japan, together more than 100 years of experience in the display industry. Again, we had the founder of Display Search and some of the early players in that company, which was I know when I was at Corning, Display Search was the authority on market research in the display industries, and so we are replicating that with the SEC. We have 9 employees. We have worked with some contractors. We're in 4 different countries. And our work, a lot of our work is around the OLED supply chain. OLED is the hot topic in the display industry, or has been for these couple of years. And so that's where we're devoting a lot of our effort in OLED supply demand, OLED materials, and the like. Our business model, we sell reports for subscription. We do custom consulting projects. We put on some events, and we do expert network consulting. In terms of events, for SID, we've organized the Display Week Business Track events. We do have a couple of upcoming events, one in California in November, and another in in Korea in December. So if you're interested in those events, you can follow the website link and look those up and register. All right, so now let's talk about the display battleground for smartphones, which is LCD and OLED. So first I'm going to just outline some of the basic principles. A liquid crystal display, as you see on the page here, has 3 main elements. The backlight, which many of you will be most interested in if you're LED experts. And the function of the backlight is just to create the light and direct it forward. Then you have a liquid crystal cell, and the liquid crystal acts as a light shutter. And then finally you have a color filter. The liquid crystal cell and the color filter are arranged in pixels. Every display, every flat panel display has pixels defined in a resolution. Typically, TV displays these days have something called 4K resolution, which means they have 4,000 pixels in the horizontal direction and about 2,000 in the vertical direction. You multiply those 2 numbers together, and a TV these days typically has 8 million pixels, and each pixel has 3 subpixels, a red, a green, and a blue. So such a TV roughly has 24 million subpixels, each of which the light output is controlled independently. The picture at the bottom, you see what is effectively 2/3 of a pixel, a red subpixel and a green subpixel. You add a blue subpixel and you've got 1 pixel. You see in the schematic, if you start from the bottom, you have the backlight. Then in the middle, you have the liquid crystal cell, which is a liquid crystal is a property of matter that it has the capability to polarize light when it's subjected to an electric field. And that polarizer combined with the lower and upper polarizers on the diagram allow you to cut off light that you don't want. You let through the light that you do want, and thereby make a picture. I think important here on this paragraph in the lower left, because the subpixel is just a light shutter, it's not consuming any power. And so the TFT circuit is just a circuit that sets a voltage. And therefore, it's a very simple circuit, and that makes the backplane, or making that circuit, relatively easier, and allows it to be much more scalable. That's different with OLED, as I'll show in a couple of slides. So on this slide, I just direct you to what are the differences in terms of the backlights, because this is LEDs magazine. Now, in larger screen LCDs, like what you'll find in TV, there are 2 different types that are used: direct lit and edge lit. Direct lit has some advantages. It allows for local dimming. In other words, you don't light the LEDs behind areas of the screen where there's no light, but then you light areas of the screen where you have peak light more intensely. And that improves the dynamic range of the picture, and improves the overall contrast and the power consumption. On the other hand, edge lit allows for a slimmer profile, allows for a thinner form factor. And though it is possible to do some dimming of things that's not so common, and because of that slimmer profile, basically all smaller screen LCDs that are used in mobile devices, and that's everything from phones to tablets to notebook computers are using an edge-lit design. And those edge-lit designs are, a critical component in addition to the LEDs and the LED line is the light guide panel, which is some extruded acrylic which guides the light and then directs it forward. Okay, now to talk about a little about OLEDs. The basic operating principle of an OLED is you have a number of organic layers, and you run current through these layers, and the layers are organized to both generate and transport both holes and electrons. You put a hole and electron together, and you get an exciton. Then if that exciton occurs in the emissive layer, you get light, and you get light of a certain color and a certain intensity. And all of those OLED materials are, let's say, very carefully chosen. There's some very complex organic chemistry involved in order to get maximum efficiency, to get the right color point, so getting a good blue, a good green, and a good red, and to get long lifetime. Now, in OLEDs are an emissive technology, and that carries with it some benefits that I'll talk about. But because of that, I'll again direct you to the paragraph on the lower left. The light output is directly related to the current in the subpixel, and the subpixel's actually doing the work to create the light. So that requires a circuit that has to set the current, and that makes a much more complex circuit and makes backplane production much more challenging to achieve high yield. So while there are a lot of companies that are chasing OLEDs, there really is only a couple companies that are doing it quite well. All right, on this slide, it just shows some of the advantages and the similarities between LCD and OLED and the differences. Similarities, they're both flat panel display technologies. They're in a matrix structure and so on. I would really more go to the differences. And the differences, the LCD has a lot more optical layers and components. So I like to refer to LCDs as macroscopically complex, whereas OLEDs with a complex circuit structure are microscopically complex. Important for this audience, the LCD uses a backlight, and the OLED does not require a backlight. Also important in terms of its use in application, OLED can be made in flexible formats and on plastic substrates, and LCD can't. And finally, it's important to understand that typically one fab or fabrication facility can make either LCD or OLED, not both. Down below, LCD's been around longer and is really the dominant technology now, but OLED is slowly gaining. For most of the display performance parameters, most people are not going to be able to tell the difference, but experts in the industry will typically tell you that OLED is the best one. On power consumption, LCD power consumption depends entirely on the backlight, and usually is independent of screen content, but OLED power consumption definitely depends on the screen content. If you have a black screen for an OLED, you have no power. And if you're in a smartphone and you're designing an operating system for OLED, you can typically get 20 to 30% better power efficiency than an LCD. But for PC like Windows page, like the one that you're looking at on this screen, OLED's going to be a lot worse because you're putting out a lot of white light. So what are we looking at for smartphones? The main things that you're looking at from a display standpoint for smartphones are brightness and power efficiency, building them into larger screens with higher resolution, getting an edge design, in other words, filling the whole device with a display so that you don't have a lot of edge, and then making it thin and lightweight. And it's those last two, especially the last one, where OLEDs are really excelling, because OLEDs have the capability of being made on flexible substrates, and that's starting to allow some new form factors. So what you have seen in the Samsung Galaxy Edge is a product where the screen curves around the edge of the phone, The iPhone, and you see in the top right picture a little profile of the iPhone 10, which uses the flexible display and curves it around to make the electrical connection, and so essentially gets the display to the edge of the device. But in the case of the iPhone 10, that device is basically still a rigid device. And we expect that Samsung, there may be some others also in the game, but we expect that Samsung will be introducing the first foldable phone either by the end of this year or early next year. On this page is our outlook for smartphone displays. We see LCD shrinking in its share of the business, and OLED growing, and a growing proportion of that being what we call flexible in the industry, or foldable in the industry. And if you download, I'm not going to go through the numbers. If you download, you can get that. So with respect to the rest of the industry outside of smartphones, the display market in terms of area is actually dominated by TVs. TVs are about 70% of area, but TVs are very commoditized, really low prices for the panels, and there's a little bit of growth, but not that much as TVs get bigger. Then you have IT applications, which is about 20% of area, also commoditized. Smartphones, which is the technology battleground. Automotive displays, which is seeing nice growth, but from a very, very small base, and has very slow moving with a long design end cycle. OLEDs are growing, but they're typically at the premium segment, both in phones and in TVs. There is a lot of flexible OLED capacity coming online, especially in China. And so if you're in the OLED business, you're looking for new ways to use that capacity, but that's slow going. OLED power consumption doesn't lend itself for traditional IT applications. It's difficult to get a price over LCD because where OLED is better, it's not that much better. So you can't charge very much of a premium. OLEDs do definitely have an advantage with flexible form factor in things like wearables and virtual reality, but these are applications that really haven't gone anywhere yet. LCDs, going back to the question of backlights, for automotive and other applications, smaller applications, basically for those applications, they're not really much different with consumer LCDs for tablets or notebooks or the like. With maybe one exception, if the form factor is not critical, you might go with a direct lit LED. Even for small LCDs, that's something that we're seeing in automotive. And there's a lot of options. You could really optimize one critical factor by sub-optimizing other factors. But when you have a specialized design like that, you typically get low volumes, and that makes the prices pretty high. All right, my last topic is MicroLED. This has been something that has been very interesting in the display industry. There's been quite some interest with the leading companies in the industry, Samsung, Apple, pursuing this technology in different ways. So first, let me first comment. What is a MicroLED? Well, if you've been in Times Square in New York, or if you've been just about anywhere in Las Vegas, you will be familiar with LED displays. Those are the big outdoor displays. Typically, those displays have red, green, and blue LEDs that are on the order of 1 millimeter to 3 to 5 millimeters of pixel size. A MicroLED is taking that and using much smaller LEDs and much smaller pixel sizes to make a display that is the size of anything from a smart watch to a large TV. And the technology, in terms of a display technology, really has a tremendous promise, but it's going to take a while for it to actually achieve some sort of volume production. On the promise side, MicroLED is expected to have up to 3 to 4 times better power consumption or power efficiency than OLED. So for portable displays, this is especially important. The second thing is that peak brightness. The macro LEDs, I'll call them, you know for having very good sunlight readability. You can see those Las Vegas displays in direct sunlight in the desert. And so that peak brightness is a real advantage in a TV-like application. Micro-LEDs should be able to get a wider color gamut and last for a long time, which is one problem that OLED has. Then in the middle, all of those performance parameters where OLED is basically as good as you're going to get. Contrast, resolution, these are things that OLED does very well. Micro-LED does just as well. And then finally on the right, things that micro-LED is inadequate is about how you can make them. Actually, bringing these to market is a big challenge. And the reason for that is that making a display requires a better LED and a better quality and better uniformity in the LEDs in terms of the light efficiency and the color point than is typical in the LED industry right now. And then the next big thing is the chip transfer from an LED wafer onto a backplane. And you need the transfer onto the backplane because the backplane is your circuit where you're independently controlling each subpixel in the display. So that chip transfer is really a critical problem and probably the biggest bottleneck into bringing micro-LEDs into the market. The third one could be a problem for very small micro-LEDs, the efficiency, and then the last, hybridization interconnects, is related to that pick-and-place problem and getting good yields. What's our outlook for micro-LED? So one of the important insights for micro-LED is that whereas OLED and LCD cost scales with area, micro-LED cost, because of that pick-and-place problem, scales with the number of pixels. And so if you know that and also know where you're adding value most in micro-LED, which is low power consumption and peak brightness, we see micro-LEDs coming in basically two places, not in phones where they're going to be too expensive for a long time. But the first place that we expect to see micro-LEDs is in something like the Apple Watch, which has a lot fewer pixels than a phone, and where you can leverage that power consumption value into really more a significantly better device. And then where we're also seeing micro-LEDs are in very large displays, where the cost in an area basis for OLED or LCD becomes untenable, and micro-LED pixel count becomes less important. And essentially that's all over 75-inch and usually a lot over 75-inch. Samsung has the Wall product, which they've recently rolled out for 146-inch display, and that goes for $385,000. One important factor in this is that anytime you're going to build micro-LED, you're going to need an advanced backplane like an OLED, and that's going to require a lot of money in either investment or conversion from existing fabs. That concludes my part of the presentation. I will certainly be available for questions. So I'll turn it back here to Maury.
Thank you very much, Bob. Now we will hear from Mike Casper of Flex. Mike, welcome.
Thank you, Maury. Thank you, Bob. Hello, everyone. And as you mentioned, I'm Mike Casper, CEO of Flex Lighting, and looking forward today to discussing some new shifts in display and illumination technologies here that are being driven mainly by some increasing diversity of device applications out there that we're seeing. Now, to give you some background on my company, Flex Lighting, we're a light guide technology company that's in the displays industry. We've been around for almost 15 years now. Our headquarters are located in Chicago, and we have sales offices throughout North America and Asia, along with several manufacturing locations. Our focus at Flex is really in providing low-power lighting for displays into a very thin light guide. Most of our products are about 50 microns thick, and this isn't just for consumer applications, but also in industrial, medical, Internet of Things, and defense applications as well. So Bob just gave you a great overview, I think, of some of today's smartphone displays and the battleground for those in the technology space. And I'm going to be touching a little bit more on how display technologies have been evolving to fit the needs of some other applications and categories of devices here moving forward. So as we know, there are billions of displays now being used throughout the world today. As consumers, most of us are familiar with those in smartphones and tablets that we're using on a day-to-day basis. But there's also this expanding number of displays starting to show up now in other applications, such as in automotive, industrial, medical, and information displays, and even signage. Product designers today now have many more options to choose from as they look to spec in a new display technology to better suit a need for a particular application. So with all these options, it's a really exciting time if you are a product designer and looking to differentiate your device. But at the same time, so many options can make it a bit confusing on where to look and what to consider. So to give you some context on really how quickly these display technologies have evolved over the past 5 to 10 years or so, it helps to take a look back on the evolution of displays over the past 100 years. Pretty much the entire 20th century was dominated by cathode ray tube or CRT displays. These are those big boxy displays that many of us grew up with. And really over that time period, beyond just adding color and some higher resolution, these didn't really change all that much over that time. But we as users didn't really care because at the time we were just amazed at the dynamic and live content we were finally able to see for the first time. Then later in the 1900s, LCDs started to emerge, and Bob gave a great overview of how liquid crystal displays work. This became a nice thinner alternative. These improved quickly to lead to these flat panel displays. They're lighter weight, they're a lot smaller, and we could easily hang them on the wall, put them on our lap for laptops, or even put them in our pockets for smartphones. The advancements of this low power computing in combination with the advancements in LEDs, especially with the low power lighting, really accelerated this adoption of LCDs in all sorts of applications during that time. And it really provided this unique combination of thinness, high resolution, full color, fast response time, and relatively low power compared to these old CRTs back then. So LCDs, they quickly overcame the older technology and became the winner in the displays race of the early 2000s. As LCD fabs expanded capacity, costs driven lower, all while performance was really advancing quite rapidly, and they became the go-to choice for really most display applications. But then, looking over the past 5 to 10 years, we've really started to see a lot more differentiation for display choices based on certain applications. So as Bob was describing, these macro LED boards started coming into play for billboards, large outdoor signage, indoor at stadiums, et cetera. But really, for longer viewing distance, it didn't matter that these LEDs were a couple millimeters apart. It still looked pretty high resolution and had some nice low power savings. E-paper displays were a big hit when e-readers first started coming out. There was a new application where the display suddenly looked phenomenal in sunlight, had a really low power draw, and while it was limited with just black and white monochrome initially, it didn't matter because it was used for books and reading applications. Additional reflective displays started showing up now more in battery-powered devices in industrial, medical applications. They started showing up recently in some outdoor consumer applications as well, where reading in the sun was very important and the reflective nature benefited those products. And then as Bob was talking about earlier, OLEDs really started making some inroads with high resolution, high contrast applications in smartphones and smartwatches like the Apple Watch as well. So today now as product designers, we have a whole host of display technologies now we can choose from across these various applications, and we're not really just stuck with a one-size-fits-all situation anymore like we may have been 20 years ago. So with that myriad of these options, though, it's sometimes confusing to keep them all organized. So we tend to bucket them in kind of 3 main types of display categories: the transmissive, emissive, and then thirdly, the reflective. So the transmissive category is really your traditional LCD. As Bob was describing earlier, the LCD pixels are essentially just shutters of light, and the backlight is generating the light through the LCD. The main reason why these are so high power draw is about only 5% of that backlight actually makes its way through the LCD pixels. So 95% of all that light generated by the LEDs and backlights are essentially wasted, and it's one of the main drivers of energy drain with a mobile type device. In addition to that, when LCDs go outside, they end up competing with the sun, and they're going to lose that battle because the sun's the most powerful light source in the world, and it really will overcome the backlight no matter how bright you pump that backlight. So I think we've all been in a situation where we're trying to read our phone while we're outside on a bright sunny day and really just struggle to see the display. Now the emissive category is really the OLEDs, the LED displays, and the micro-LEDs, as Bob was describing earlier as well. These illuminate these images by applying a charge to the display, and while sometimes they are more energy efficient than these traditional transmissive LCDs, they still do have to compete with the sun, and the brighter the sun, the more power you're going to have to pull on those displays in order to overcome that brightness. Now the third category here is reflective LCDs. They essentially have pixels just like traditional LCDs. They're made on the same fabs. However, the backlight is taken out and it's replaced with a mirrored layer. This layer ends up reflecting ambient light off the top of the display. So it saves a pretty significant amount of energy, and it ends up using the bright sun and brighter ambient lighting to its advantage when it's in those environments. So here in the reflective category, the brighter the sun, the less energy is consumed. And the main types that really fall into this category are these reflective LCDs and e-papers, as I mentioned. So the recent attention, that we've been giving to OLEDs and the growth that Bob was showing there, the potential for micro-LEDs in the future, and the recent growth in reflective LCDs all have one thing in common, and in the end, they're getting rid of the backlight. So the backlight industry, I think we're going to see that continue to shrink because of these new display technologies. In other words, I don't think the future is too bright for backlights moving forward. So now the good news is that there still is a lighting requirement with reflective LCDs. While these displays look great in the bright sun, there are still instances where a user may be walking into a low lighting condition or they're trying to look at the display in the dark. And since you don't have a backlight there anymore, it's really difficult to see. So since the backlight doesn't work with these types of displays, there's an alternative known as a front light, which is used. Now this is essentially a light guide that's placed on the top surface of the display. It couples into an LED, and then it directs the light downwards towards the display. It bounces through the pixels of the LCD, hits that mirrored surface, and then reflects back up to the user to still deliver that color and the illumination in order to see the display. It doesn't produce any haze, though. When you're in a really bright environment, you can turn the front light off, use the sun to your advantage, and because the front light can be crystal clear, it doesn't introduce any other defects or imperfections into viewing the display. Now, reflective displays end up having a host of new benefits really for product designers to consider beyond the traditional transmissive LCDs, OLEDs, and even some of the potential micro-LEDs. Because there's no backlight and the display mainly uses ambient light for illumination, there's really a tremendous amount of energy savings that can be captured. And we're talking about 80 to 90% improvement in some applications. I'll walk you through a recent case study here in the next slide shortly to show this. Also, because there's no light source shining directly into your eyes, as typically found in backlit LCDs or in OLEDs or micro-LEDs, there's some health benefits as well that come into play with reduced eye strain with reflective LCDs. If you think about it, humans for thousands of years here, we've been so accustomed to seeing things in a reflective nature. The light is reflecting off objects, and that's what allows us to see it. So our body is much more attuned to receiving reflected light versus LEDs shining directly into our eyes. With that, reflective displays, as I mentioned earlier, also provide some improved outdoor readability. The brighter the sun, the less amount of additional lighting is needed and the better the display looks. And so this is really a 180 from what product designers have had to deal with in the past, where you're forced to pump backlight 10,000 nits or more to fight the sun, and OLEDs and micro-LEDs still have that challenge. And then finally, there's the reduced materials. By taking out the backlight, by taking out all those optical films and back reflectors, on all those LEDs in transmissive LCDs, you now can reduce some of those materials. You can minimize the number of optical films on the top and minimize the number of LEDs used as well. So these are really some added benefits that offer some new considerations for many product designers today. And what we've been hearing recently is that the most impactful benefit they're seeing has really been in this energy saving. So one example was a case study we looked at with a handheld device manufacturer. It was for an industrial application for metering, and it had a display for the user. They were considering using either an OLED display or a reflective style display from either e-ink or Sharp in this particular application. This design was the screen for this use case was being updated about once every 10 seconds on average, and they had a design-in capacity for a battery of about 3,000 milliwatt hours that they were hoping to use. So we ended up working to measure that energy drain on the battery from just the display itself. And as you can see in this chart here, the OLED display shown on the blue line on the left drained this battery pretty quick. It's pretty much under 10 hours of use had drained that entire battery. The e-ink display with the front light, as shown in the green line there, lasted over 90 hours on that same battery, so a pretty significant improvement. And then that Sharp reflective display with the front light as well got even a little bit more, up to 100 hours of use. So it's a 10x improvement over the OLED that was being looked at, and quite a new feature that enabled this product to offer it to their users in that industry. So as you can see here, reflective displays kind of offer a new lever that's available for product designers to enable some new applications. Handheld devices can now last several days on one charge. IoT devices, which previously never been fathomed adding a display in their design because of the power drain, they can now consider it and put a display in without serving too much of a power drain on the battery. And then also in some of the recent accelerated improvements we've seen in color quality, the resolution, the high contrast with these reflective LCDs. We're now seeing even some tablets and other consumer type devices looking at reflective LCDs for better design options moving forward. So here's some additional comparative information, if you will, as seen by BOE. BOE is one of the largest LCD manufacturers in China, and the blue line here shows what the view of the traditional backlit LCD is. Again, like we've talked about, it provides great color, great dynamic video. However, we've discussed it falls pretty short in outdoor readability and with the health impacts due to the eye strain. Reflective LCDs, as shown in the red, use those same LCD fabs as traditional LCDs, so they're able to still get the great color, the great dynamic video, and to scale in area size, but they also have this additional advantage of low power, outdoor readability, and reduced eye strain. So when you start to include OLEDs and micro LEDs into the mix, there's also several differences here that stand out when you compare all these display technologies across them. So as Bob described earlier, OLEDs and micro LEDs have this phenomenal color, high contrast, deep blacks, and can do this dynamic video, but they can't quite match the production capacity that traditional LCDs have amassed over the past 20 or so years, which also comes into play with the cost structure between those technologies. With micro LEDs showing some promise for these improvements in low power and outdoor readability, but we're still a ways off. And I think one critical piece here that's really not on this table is cost. I think for many designers, looking at a micro LED display at 4 to 8 times the cost of an OLED is typically a non-starter to even consider that for most device designs. When you look at e-paper, as we've seen in most e-readers, offers some great low power benefits and outdoor readability, but has nowhere near the same color or video capability we're used to in most of these dynamic display applications. So they've been showing some improvements recently in color, but it's really nowhere near the levels of LCDs and OLEDs that we've seen recently. And then finally, reflective LCDs, as I've discussed, especially those that have the proper front lighting, they do offer a nice combination of benefits. Uses the same LCD fabs as traditional transmissive LCDs, allows them to get this great color, high resolution, and dynamic video. By taking out that backlight, provides some lower power and reduced eye strain. So all of these are becoming more important for various applications and giving these more options for designers to choose from as they're looking at the next display technology to integrate in their device. So we're seeing the new reflective style LCDs being considered more and more for a variety of applications, mainly in what's shown here on the screen, for wearables, for medical devices, for industrial, handheld or outdoor applications, for IoT devices, and as I mentioned, they're even starting to show up in more traditional consumer electronic devices and even in some outdoor signage. So the advancements we've seen here in display technologies and illumination technologies, even the past year or two, have really opened the door for new options and product features. And it really is an exciting time for anyone looking to design in electronic devices in the future. So I just want to thank you for your time here today. Please do reach out to me if you have any questions you'd like to discuss offline. I've got our contact information here, and then also our website online provides some further information as well. So I think now we're going to pass it back over to Maury and open it up to the audience here for any questions.
Thanks, Mike, for a very good presentation. Invariably, we will get a question or two about the PDFs of these presentations, and as I said up front, you are free to download these presentations. There's an area to the lower left of your screen that says Event Resources. If you just go down to there, there's a drop-down menu that will allow you to download the PDF. So starting off, Mike, you talked a lot about reflective LCDs, and obviously you guys are the maker of a light guide, but not of the display. So who are the major suppliers developing the actual reflective LCD panels?
Yeah, we've seen Sharp Electronics was really one of the more recent foray, kind of the first ones into the industry with some of their reflective LCDs. Japan Display, otherwise known as JDI, they also have a line of reflective LCDs. And then BOE and Tianma have recently shown some really nice displays at CES this past year, and then also at SID's Display Week in May. So pretty much, now most of the major LCD players in the industry have converted some of their fabs over to this reflective style, just because it is pretty straightforward in taking that the existing fabs and switching them to this reflective style.
Bob, we have a couple of questions about OLEDs, and one is very general. How are OLED mechanics different for TVs versus handsets? I mean, there's obviously a size issue there, but I think this person was looking maybe for more of the finer details of what's different.
Yeah, sure. Because OLEDs in TVs and in phones, they're both called OLEDs, and they both have the same operating principle, but really at what I would call the product architecture level, they're very different. Let's say a couple of main differences. Handsets are dominated by Samsung. Samsung has been able to make them cost effectively and actually makes good money on OLED phone panels. And Samsung has, because they're making profits, has a lot of followers. OLED TV panels are dominated by LGD, and I sometimes say LGD is not the leader in OLED TV; they're the only, because they've struggled to make them cost effectively, and they don't make a profit on those panels, and so they don't have any followers. Aside from the size difference, one of the important differences is that in TV, LG's chosen a product architecture called white OLED. They actually have 4 subpixels in every pixel: a red, green, blue, and a white subpixel. And essentially, they in their design, they're creating white light with the OLED stack, and then they have a color filter in front, filtering that out. And there are a whole variety of reasons why they're doing this that go beyond the scope of a webinar like this. But that's suboptimal from the standpoint of both cost and performance, especially performance with respect to power efficiency and peak brightness. Having said that, it's still the best looking TVs out there, I would say, but they really struggle to make it cost effective. I would say one of the other big differences with handsets is many of the handsets of OLED are made on what we refer to in the industry as flexible OLED substrate. So the substrate itself is actually plastic rather than glass. And that gives the potential for making it into some sort of foldable design.
So, Mike, here's a question talking about use of a reflective display indoors. And the attendee says, for the reflective LCD in a dark room, how will it work? What will the light source be if the room is dark?
Yeah, and that's really where, in the reflective LCD, the backlight doesn't work. And so it really needs a front surface illumination source in order to see the display. That's where, taking a light guide and it's similar to a backlight light guide, but there are some differences in terms of how it's designed and how it's implemented. But essentially, it's a light guide that's placed on the front surface and illuminated. The key challenge is really driving the light towards the display, bouncing off that reflective mirror and then illuminating enough to see it. So if you've ever seen like one of the Kindle Paperwhites recently, those do have a front light that is on the front surface, and it will shine light on the display to see it in a dark environment, as an example.
And does that front light turn on dynamically based on the ambient conditions?
It can, yeah. Ultimately, it's how the end device and the use case would get designed into it. There could just as easily be a sensor, an ambient light sensor designed into the device that would adjust the LED brightness of the front light depending on the environment. But the good thing is that because the reflective display, the reflective LCD, is such a low power consumption, and the front light is also very low power consumption, you could arguably put the front light on in all conditions and still have a pretty significant energy savings compared to backlit LCDs.
Here's another question about the very large TVs, and obviously an interesting application for consumers. Samsung has said they will launch a consumer version of the wall TV next year. Play Nitride claims they can do a 75-inch panel. Why won't this be very expensive like the current wall TVs, since it will have the same pixel count?
Sure. That's a very good question, and it brings up a very interesting point. Indeed, I have seen this report that Play Nitride is talking about a 75-inch panel. And essentially my answer to their question, why won't it be very expensive, is it will be very expensive. And I think that this report is actually likely to be mischaracterizing a potential future product, because it will be very expensive to make a high resolution micro LED. So the likely places where you're going to sell it are in the very large sizes. Note that 75-inch TV is not something that Samsung announced, but that Play Nitride might be talking about. Now, what might be a source of confusion is that some of the Samsung products have micro LED backlight units. So they may have an array of micro LED backlights that might be, for example, 10,000 micro LED backlights in a 75-inch TV. That allows for very good local dimming control, really gets you very good contrast and so on, but it's not the same as a true micro LED display. It's a micro LED backlight, and so that can be a source of confusion, and I think that's actually what's going on in this case.
In another question about the reflective displays, although I think it's pretty much the same question as we had you answer before, Mike, but the maybe I'll add something to it, because the light guide is on the front, and you talked about it does work similar to backlights, but I've also seen some talk of displays that would use both a front and a backlight. Can you address that? I guess that would really be cost prohibitive and would erase your power savings.
Yeah, and what you might be referring to is often called a transflective display. It's almost a hybrid of that transmissive traditional LCD and this new reflective style. And transflective, when they first came out, we're kind of being praised as this great you could put a backlight on and it could look good in the sun. I think in reality, it ended up being worse in both environments because the backlight drain was even higher and the reflectivity outdoors was pretty low, so it didn't even look that great. So in terms of front lighting, it is a pretty significant difference in terms of you can't just take a backlight and slap it on top of a display and suddenly make it a front light. I think Bob showed a slide earlier in his presentation where backlights typically have diffuser films, there's brightness enhancing films, there's back reflector films, there's a whole host of other optical films that have to go in there, and it makes it a pretty loose light control, light guide, I'll call it. Front lighting, on the other hand, because you're now between the user and the display, front lights have to be crystal clear and they have to have light extraction features that are much smaller than the pixels of the display so that doesn't distort the image. And so you can't have optical diffusers, you can't have BEF films and back reflectors when you use a front light design. So there are some optical design elements you have to take into account when front lighting that make it a little bit more challenging for reflective LCDs.
Clearly MicroLED technology has some allure, and that's not to say that the technologies we have today aren't very good, because most of us couldn't live without them anymore now that we've had them. But in terms of MicroLED, and maybe both of you could comment on this, but is there a way around the manufacturing problem? I mean, could you do something at the semiconductor processing level, maybe at the wafer level, or is there another approach? I've heard about multiple approaches to kind of the pick and place problem, but is there a technology hiding out there that maybe would solve what I see as the biggest hurdle for them?
Let me start with that one. Good question. If it's out there, it's hiding. Apple, the place where it's most likely to be hiding, I would say, is at Apple. Apple acquired a Taiwanese company that was with expertise in micro-LEDs a few years ago, and they've been working on it since. That's why we expect the Apple Watch to be a micro-LED starting next year. But if there's a breakthrough, and probably people on this call all recognize Apple as a notoriously secretive company. So the notion that there might be some sort of secret that they're holding that could lead to a breakthrough is possible, but that's maybe someplace where you'd see it. It's a tremendous challenge because effectively you're trying to take something from a wafer size to something let's say much larger than that. Combining the colors, you've got to get red, green, and blue, and so on. There's a number of different approaches, but it's not immediately apparent that there is that magic bullet yet.
Mike, anything to add to that?
Yeah, I agree with Bob, and then also the factor of dollars. I mean, I think billions of dollars in really just changing the manufacturing approaches are going to be required in order to get that, and I still struggle to see how yield will be solved. Imagine a couple of these small LEDs going out in a display would suddenly cause the whole display to be defective. So there's a host of challenges and beyond some secret technology that's lurking out there and a whole lot of dollars, I struggle to see that as well.
Mike, here's another question about the front lighting. This person says, could the film cause any image distortion when it is in the off state?
Yeah, so I'm assuming when the front light is in the off state and the display is still on, so I'll assume that's part of the question. But if you just took a standard acrylic injection molded backlight and try to place it on the top surface of some of these newer higher resolution reflective LCDs, it absolutely would cause a lot of distortion. I think that's the big challenge when you look at how do you front light it. you have to make sure that the light guide is very, very thin, and that the light extracting features that are embedded in that light guide have to be smaller than the pixels. Unless you can do that, it will cause distortion. So at least with some of our products we have at Flex, we're able to use 50 micron light guides, so we're extremely thin, and our light extractors are significantly smaller than the pixels of the display, so we don't cause any distortion on those.
Also, for you, Mike, have you seen any current automotive applications, and I assume they mean using reflective displays?
Yeah, that's also getting some interest. I can't really comment on any specific customer at the moment, but it's been getting a lot more interest, and even in just very thin and flexible lighting applications, not necessarily related to displays, but also as automotive designs are changing with the future of that industry, being able to provide thin, flexible light guides is an emerging application for us as well.
One other technology, which is really an adjunct to some of the things that were talked about today, and I think I did see this on one of Bob's slides, but I don't believe, Bob, you mentioned it, but maybe either of you might comment on it. What about quantum dot technology and what it brings to the table, either in a kind of a backlighting role or in some other manner?
Sure. So yeah, quantum dots is an interesting technology development. So quantum dots are a kind of material where they will absorb energy and emit light in a very narrow spectrum and highly efficiently. So you have very high quantum efficiency of the light output. They are used in TVs today. So Samsung's what they refer to as QLED products are using quantum dots. Now, in that case, they're starting with a standard LCD backlight, LED backlight. But rather than having a white backlight, which is based on blue LEDs with typically a yellow phosphor on top, they're simply going with a blue backlight, which is based on blue LEDs, which is typically the starting point for the LED backlight anyway. And then they put a quantum dot enhancement film in the backlight stack, and that enhancement film has quantum dots and converts. You have red quantum dots that convert the blue light into red, and you have green quantum dots that convert the blue light into green. And so then what comes out of the quantum dot enhancement film in the stack is white. So Samsung has that product. There are a few other brands, TCL and a few others that have that product as well. And so it's going to be a force in the TV part of the business for the next several years. Samsung's also pursuing something that we refer to as QD OLED, quantum dot OLED. And they would be using a similar approach where they will be essentially making a blue OLED. So not essentially making an OLED that's a little bit like a backlight, but does have at the sub level a pixel structure. But in those, each of the subpixels at the OLED stack is only putting out blue, but then they put in front of it what they're referring to as a quantum dot color converter. So essentially what you want to do is to convert the blue light into green and red using quantum dots. It's got a lot of promise. There's some start in using it in TVs. But there's a lot of technology development to figure out how to make use of the new technology in both a high performance way and a cost effective way.
And Mike, is there any play with quantum dots kind of at that industrial Internet of Things area, or is that's really just not something that would be applicable there?
Yeah, not really. I mean, unless it's embedded in the backlight, like Bob was just describing there. And I think where quantum dots made some improvements in color recently, and probably will for a couple of years here still, really when you look at fundamentally, though, anytime you're converting color for these LEDs, there's some loss associated with it. And as LEDs continue to improve in efficacy, the ideal situation for color is just having the red, green, and blue, no phosphor converted white, and just having the raw LEDs and being able to color mix those properly. So getting the right optics associated and mixing those is the fundamental kind of best, lowest energy use case scenario. But probably not necessary for a few more years here as LEDs are continuing to get better and better efficacy.
So we're at the top of the hour, but I do have to ask one other quick thing, and it's probably subject for another venue, whether it be an article or a webcast or whatever. But Mike, I can't help but wonder about how else you might use your light guides, because they do produce white light, and of course a lot of the stuff we write about has to do with producing white light for things like general illumination. Is that at all an application that you can impact?
Yeah, no, absolutely, and just with our flexible light guide, being able to take LEDs, which are still some of the best lumens per watt components out there, and especially from a cost standpoint, being able to channel that light into very thin and flexible panels has proven a lot of interest in the lighting industry. So I think general lighting applications, new designs for architectural and other commercial lighting fixtures, something that we're pretty excited about into the future. We're pretty heavily focused in displays today, but general illumination is an area that we're expanding into as well as the automotive, as I described earlier.
Okay, very good. Well, we are past the top of the hour, so I'm afraid we'll have to end here. On behalf of LEDs Magazine and Pinwheel Corporation, I'd certainly like to thank Mike, Casper, and Bob O'Brien for excellent presentations today. And I'd like to thank Flex Lighting again for making this presentation possible. The webcast, Display Industry Reflects an Application-Driven Shift in Illumination Technologies, will be archived within 24 hours. It can be accessed from the homepage at ledsmagazine.com, and we'll send all you registrants a direct link. Most of all, I want to thank you in the audience for joining us. I know your time's extremely valuable. We always appreciate it when you spend some of that time with us, and we certainly look forward to serving you with future webcasts. Have a great day.